Welcome to Spotify for Podcasters.
Hi everyone, welcome back to our new special series for Intermolecular Forces podcast. And today, we will discuss state of matter, intermolecular forces, van der Waals forces, and under it are ion-dipole interactions, dipole-dipole interactions, hydrogen bonding, London dispersion forces, and also we will summarize intermolecular forces and Bell-work intermolecular forces.
The fundamental difference between states of matter is the distance between particles. In gas, the particles in the state move freely due to much empty space. In liquid, particles in the state move freely yet only move in the space they were contained. And in crystalline solid, particles in this fixed position due to the reason that they attract each other in the state. Here on this slide, you can see that the solid and liquid state are close together, and we refer them as condensed phases.
The state of a substance is in a particular temperature and pressure depends on two antagonistic entities. First, the kinetic energy of the particles. Second, the strength of the attraction between the particles. So what is intermolecular forces? The attraction between molecules are not nearly as strong as the intramolecular attraction that holds compounds together. They are, however, strong enough to control physical properties such as boiling and melting points, vapor pressures, and viscosities. These intermolecular forces as a group are referred to as van der Waals forces. The forces are named after Dutch physicist Johannes Diederik van der Waals, who in 1873 first postulated these intermolecular forces in developing a theory to account for the properties of real gases. Strength of IMF depends on the following. First, arrangement of the particles. Second, proximity of particles relative to one another. Third, the nature of the interacting particles.
Ion-dipole interactions. A fourth type of force, ion-dipole interactions are an important force in solutions of ions. The strength of these forces are what makes it possible for ionic substances to dissolve in polar solvents.
If the molecule is an anion, it will be attracted to the partially positive end of the polar molecule. If the molecule is a cation, it will be attracted to the partially negative end of the polar molecule.
Dipole-dipole interactions. Molecules that have permanent dipoles are attracted to each other. The positive end of one is attracted to the negative end of the other, and vice versa. These forces are only important when the molecules are close to each other. The more polar the molecule, the higher is its boiling point.
Dipole-dipole interactions are observed in polar covalent molecules, such as amino acids, wherein the electrons are shared by both oxygen and carbon atoms. An increase in temperature diminishes the strength of a dipole-dipole interaction, which may explain the observed volatility of certain polar covalent compounds, such as sulfur dioxide.
London dispersion force. While the electron on the first s orbital of helium would repel each other and therefore tend to stay far away from each other, it does happen that they occasionally wind up on the same side of the atom. At that instant, then the helium atom is polar, with an excess of electrons on the left side and a shortage on the right side. Another helium nearby then would have a dipole induced in it, as the electron of the left side of helium, atom 2, repel the electrons in the cloud on helium atom 1. London dispersion forces, or dispersion forces, are attractions between an instantaneous dipole and an induced dipole. These factors are presented in all molecules, whether they are all polar or non-polar. The tendency of an electron cloud to distort in this way is called polarizability.
Factors affecting the London forces. The shape of the molecule affects the strength of dispersion forces. Long, skinny molecules like N-pentane tend to have stronger dispersion forces than short, fat ones like neopentane. This is due to the increased surface area in N-pentane. Strength of dispersion forces tends to increase with increased molecular weight. The large atoms have larger electron clouds, which are easier to polarize.
To summarize the London dispersion force, one molecule with a temporary dipole exerts a weak attractive force on another pole. Note that London dispersion force is the weakest among the intermolecular force because the force is easily broken. However, the more electrons a molecule has, the stronger the London dispersion forces are.
Watch this short video to get 30 minutes of uninterrupted listening.
Practice exercise of 2-bromine, neon, hydrochloric acid, hydrogen bromide, and 2-nitrogen, which is likely to have A. The largest intermolecular dispersion forces, and B. The largest dipole-dipole attractive forces. To identify which of the following has the largest intermolecular dispersion forces, you need to calculate their molecular weight, and the one that has greater molecular weight will have the largest intermolecular dispersion forces, since the strength of dispersion forces tends to increase with increased molecular weight. So, if you calculate their molecular weight, the 2-bromine will have the greater molecular weight. So, our answer will be the 2-bromine. The next question is, which is likely to have the largest dipole-dipole attractive forces? Hydrochloric acid is most likely to have the largest dipole-dipole attractive forces because the hydraulic acid contains one atom of hydrogen and one atom of chlorine. Chlorine is going to pull that electron towards itself, and so it's going to have a partial positive and negative charge. The positive charge is going to be where the hydrogen is, and the negative charge is going to be where the chlorine is. And if we have two of these, we will certainly get the dipole-dipole forces.
Enjoy the next 30 minutes of uninterrupted listening.
Which have a greater effect, dipole-dipole interaction or dispersion forces? If two molecules are of comparable size and shape, dipole-dipole interaction will likely be the dominating force. If one molecule is much larger than other, dispersion forces will be likely determine its physical properties. So how do we explain this? The non-polar series thionine to methane follow the expected trend. The non-polar series follow the trend from hydrogen telluride to hydrogen sulfide, but water is quite an anomaly.
The dipole-dipole interactions experienced when H is bonded to N, O, or F are unusually strong. We can call these interactions hydrogen bonds. Hydrogen bonding arises in part from the high electronegativity of nitrogen, oxygen, and fluorine. Also, when hydrogen is bonded to one of those very electronegative elements, the hydrogen nucleus is exposed.
Watch this short video to get 30 minutes of uninterrupted listening.
Practice exercise. In which of the following substances is significant hydrogen bonding possible? Methylene chloride, phosphine, hydrogen peroxide, or acetone? Among the substances, the hydrogen peroxide is the only compound that contains hydrogen bonded directly in oxygen, which means the hydrogen peroxide is likely to form hydrogen bond.
Summarizing intermolecular forces. Polar molecules is not involved in dispersion forces only or induced dipoles. Polar molecules are involved in both dipole-dipole forces and hydrogen bonding. But only in hydrogen bonding, hydrogen atoms are bonded to nitrogen, oxygen, and fluorine atoms. Polar molecules and ions are both present in ion dipole forces, but in ionic bonding, only the ions molecules are present. Example of dispersion forces only are argon and iodine. Example of dipole-dipole forces are hydrogen sulfide and chloromethane. Example of hydrogen bonding are liquid and solid water, ammonia and hydrogen fluoride. Example for ion dipole forces is potassium bromide in water. And lastly, example for ionic bonding are sodium chloride and ammonium nitrate.
Practice exercise. A. Identify the intermolecular forces present in the following substances, and letter B. Select the substance with the highest boiling point. Given the following substances: ethane, methanol, and ethanol. In ethane, the intermolecular forces that is present is only the dispersion forces, since it is a nonpolar compound. In both the methanol and ethanol has the dispersion forces and hydrogen bond, since these are compounds with hydrogen bonded in oxygen and a polar compound. The ethanol has the highest boiling point, since hydrogen bond is present in this substance. Although the methanol has hydrogen bond, but when you calculate their molecular mass, ethanol has greater molecular mass than methanol. So with that, the ethanol has the highest boiling point among the substances.
Enjoy the next 30 minutes of uninterrupted listening.
Intermolecular forces affects many physical properties. The strength of the attractions between the particles can greatly affect the properties of a substance or solution. Viscosity. Resistance of a liquid to flow is called viscosity. It is related to the ease which molecules can move past each other. Viscosity increases with stronger intermolecular forces and decreases with higher temperature. Surface tension. Surface tension results from the net inward force experienced by a molecule on the surface of a liquid.
Many important properties of liquids and solids relate to the ease with which they change from one state to another. Everyone has seen examples of such changes. Water left uncovered in a glass for several days evaporates. An ice cube left in a warm room quickly melts. Solid, CO2, or solid as dry ice, sublimes at a room temperature. That is, it changes directly from solid to the vapor state. In general, each state of matter can change into either of the other two states. The figure below shows the name associated with each of these transformations. These transformations are called phase changes or changes of state.
Each phase change is accompanied by a change in the energy of the system. Whenever a phase change involves going to a less ordered state, energy must be supplied to overcome intermolecular forces. Thus, energy is required to melt a solid. The attractive forces that hold particles in fixed position in the solid must be overcome to form the liquid. Likewise, vaporization requires energy. The attractive forces that hold particles close to each other in the liquid must be overcome to form the gas. Sublimation also requires energy. As the strength of the intermolecular forces increase, the amount of energy required to cause a phase change also increase.
Heat of fission, energy required to change a solid at its melting point to a liquid. Heat of vaporization, energy required to change a liquid at its boiling point to a gas.
Heating curve for the transformation of 1 mole of water from negative 25 degrees Celsius to 125 degrees Celsius at a constant pressure of 1 atmospheric pressure. Blue lines show the heating of one phase from a lower temperature to a higher one. Red lines show the conversion of one phase to another at constant temperature. We can calculate the enthalpy change of the system for each of the segments of the heating curve. In segments A, B, C, D, and E, F, we are heating a single phase from one temperature to another. The amount of heat needed to raise the temperature of a substance is given by the product of the specific heat, mass, and temperature change.
The greater the specific heat of a substance, the more heat we must add to accomplish a certain temperature increase. Because the specific heat of water is greater than that of ice, the slope of segment CD is less than that of segment AB. We must add more heat to water to achieve a 1 degree Celsius temperature change that is needed to warm the same quantity of ice by 1 degree Celsius. In segments BC and DE, we are converting one phase to another at a constant temperature. The temperature remains constant during these phase changes because the added energy is used to overcome the attractive forces between molecules rather than to increase their average kinetic energy. For segment BC, in which ice is converted to water, the enthalpy change can be calculated by using heat fusion, while for segment DE, we can use heat of vaporization.